Okay, let's continue. And I continue with an example on the Gram-Smith algorithm from R4. And I'm given these three vectors. Like this, and they are linearly independent. And you know how to investigate for linearly independency. That you simply take, take the coordinate matrix for this one, and then you find the rank of that matrix. And if it is 3, then they are linearly independent, or the determinant. No, this is not square, so you cannot compute the determinant. Okay, this is linearly independent. So I choose this as my first vector, and in order to get a unit vector, I norm it. So the first vector in my set will be u1 divided by the length of u1, and the length of this one is 1 squared plus 1 squared plus 1 squared plus 1 squared. That is 4. The square root of that is 2. So I have the vector 1/2, 1/2, 1/2, and 1/2. So this is my first unit vector. Now I want to proceed with this formula here, and I use this formula with p equal to 2. So I only have to consider the subtraction of this first vector here. So I have that my second candidate for this orthonormal basis is this vector here, which is 1. Let me write it as columns this time, because this is more compact then. And then I should subtract the scalar product between this vector here, which is 1, 0, 1, 0, the scalar product, and this first vector here, which is 1/2, 1/2, 1/2, and 1/2. And then I should multiply it with this unit vector. Now the scalar product here is 1 times 1/2 plus 0 plus 1 times 1/2. That is 1. So the scalar product here is 1. So you have to subtract 1/2 from here. You get 1/2. And 0 minus 1/2, that is minus 1/2. And then minus 1/2. So this is my second vector. And now I really have to norm it. But you see, this is, it's only a change of sign, so the length of this vector here will be 1. So I have that my second unit vector is 1/2 minus 1/2, 1/2, and then minus 1/2. Okay, now I'm going to continue with with V3. And I get that W3. And here I take the third vector U3. Again, I write it as columns. 1, 0, 0, 1. And then I subtract the scalar product between this vector here and the first unit vector, which is 1/2, 1/2, 1/2, 1/2, and then times, this is the scalar product, and then the vector. But now you also have to subtract the scalar product times the second vector, and this vector is 1/2, minus 1/2, 1/2, and minus 1/2. Then this should be multiplied by 1 minus 1/2, 1/2, and minus 1/2. Here you have the scalar product of these two, and you have 1/2 plus 1/2. This is equal to 1. Now the scalar product of these two, 1/2 and then minus 1/2, is equal to 0. So my vector is already perpendicular to this vector here. So I need not take this. And then let me see what happens. I get 1 minus 1/2. That is 1/2. And then I get minus 1/2, minus 1/2, and 1/2. Again, I have to norm this vector, but we know that the length of this vector here is 1. So you get that V3, I could write it. And since this is 1, then it's equal to V3, and this is then equal to 1/2 minus 1/2 minus 1/2, 1/2. So in this way I have the three normed orthogonal vectors that span the subspace that is also spanned by U1 and U2 and U3. You know, if you have a set of linearly independent vectors and you look at the span of these vectors, it will be a subspace. And now I have constructed, by this algorithm, I have constructed an orthonormal basis for this subspace. Now to some definitions. I say a matrix Q whose columns is an orthonormal basis. Is called, yeah, what do you think it is called? A matrix whose basis is an orthonormal basis. What is this matrix called? is called orthogonal. And this is a bit weird, but this is the tradition. You would, well, it would be more natural to call it orthonormal, because the basis is orthonormal. But all the basis vectors are orthogonal, but they also have unit length. But it is a tradition, so all the literature will call this orthogonal, and so do we. So let me continue over here. Now, let's suppose that Q, this vector Q here, can be written in this way. You have a vector in, or the first column vector called V1, and then you have the second column vector, and and then you have the third column vector like this. Now we assume that this is orthogonal. And what I then do is that I form this matrix product. I take the transpose of the matrix Q and multiply it to the matrix Q. So let's see how that looks. Imagine when you take the transpose of a matrix, you interchange columns and rows. That is, the first column vector here becomes the first row in the transposed matrix. So let me write this in the following way, that I have here the first row, which is V1, and then the second row. And here you should imagine this as a horizontal vector. I could write a T for the transpose of this vector, so you think of, I have written V3 here. It should be the general case, so it's n-dimensional. So here you have the transpose of Q. Now multiply this with V1, Vn, these vectors here. What do you get? Remember, when you look at a specific matrix product, then if you have, say, the first entry here in the product, then this will be the product of the first row in the first factor with the first column. That is the scalar product of this vector times this vector. And the second position here, you have the first row here, you are in the first row in the resultant matrix, and then the second column but your V's are orthonormal. So this product will be 0, and so will the third, and so on. All other entries in the first row will be 0 because the vector v1 is orthogonal to all the other vectors. When you go down here to the second row, you have that the first position here will be this vector here times the first vector here, but again they are perpendicular, so, or orthogonal, so this is 0. And now for the second position here you get v2 times v2 and then 0. And you can continue this scheme and you get, and then finally here you get the nth row here times the nth column, so you will get Vn times Vn. But you know that this scalar product here is the length of the one vector times the length of the same vector, and this is 1, and then cosine to the angle between the two vectors, but since it's the same vector, the angle is 0, and so this is 1 times 1 times 1, it's equal to 1. So all the diagonal entries here will be 1, so this is simply the identity matrix En, where you have ones in the diagonal and 0 elsewhere. But this is truly nice, because what you see here is that you have this matrix times Q is equal to the identity matrix. This means that this will actually be the inverse of Q. So instead of solving to find the inverse, you just take the transpose of the matrix, which is much easier. So for an orthogonal matrix, you have that, this is of course correct, but you have that the inverse of the matrix is equal to the transpose of the matrix. Okay. So let's continue with symmetric matrices. I'll just give a general definition in R3 of such a matrix. You have A, B, C, and being symmetric, you have B here, and then you have D, E, and then you will have E here. No, you will have C here and E here, and then you could have some new value here. So you see, the elements in the diagonal doesn't matter. But what is important, that is, if you reflect here in this line here, you have the same value in the matrix. So let's try to take the transpose of this matrix. And you get the transpose of a matrix by interchanging rows and columns. So here you have A, B, C. You have B, D, E, and here you have C, E, F. Okay. What you can see here is that this is, of course, the same matrix as this one due to the symmetry. So these are equal. And this leads to the definition of what a symmetric matrix is. I can give you the definition here. Symmetric matrices, they always fulfill that the transpose of the matrix is equal to the matrix itself. Now we have reached the nice properties. Of symmetric matrices. So here I list the properties for a general A in Rn, and here I take a symmetric A in I should of course write Rn cross Rn and Rn cross Rn like this. A has n eigenvalues. We saw that, and it could be real or it could be complex, or but it always have n eigenvalues. You should calculate it with multiplicity. But the nice thing about symmetric matrices is it has n real eigenvalues. Now, you will work with that in the exercise this afternoon. There's an exercise where you, for a 2x2 matrix, shall prove that the eigenvalues actually are real. Now, eigenvectors corresponding to different eigenvalues are linearly independent. We saw that. But here, for a symmetric matrix, you have that eigenvectors corresponding to different eigenvalues values are orthogonal. And this means if you have n different eigenvalues, then you have n different eigenvectors, and they are all orthogonal. So in order to get an orthonormal basis, then you just have to norm these vectors. Now, on occasion here, you have that the geometrical or the geometric multiplicity of an eigenvalue, or the sum of these, are less than or equal to the algebraic multiplicity. And in the case where you have a geometric multiplicity that is less than the algebraic multiplicity, then you cannot find n different or n eigenvectors that are linearly independent. And you cannot diagonalize the matrix. This is what we saw for the general matrices. But for symmetric matrices, you always have that the geometric multiplicity is equal to the algebraic multiplicity. And this means that A can always be diagonalized. The final, let me see if I can fit this in here. The final one, in the event that the geometrical or the sum of was equal to the sum of the geometrical multiplicity of A, and this is of course equal to n, then you could diagonalize the general matrix, and you had this relation where the diagonal matrix was equal to this factorization of A, where V is the set of eigenvectors corresponding to the eigenvalues, and it has to be in the same order as the diagonal elements here, and so forth. But you saw this. Now for a symmetric matrix, this is much stronger, because here you have that this diagonal matrix is, you could write it as an orthonormal matrix, and then times the matrix Q. And here I said it, which was wrong. Q is orthogonal and not orthonormal. You can write it in this way. Okay. These are the specifics about symmetric matrix. With the property 1, you're going to try that out in one of the exercises this afternoon with the 2x2 matrix, so I won't go into that. But I will prove to you that the eigenvectors corresponding to different eigenvalues are orthogonal. So here I write proof of 2. Now, here we have one eigenvector of this symmetric matrix X corresponding to the eigenvalue lambda 1. And here you have another eigenvector corresponding to lambda 2, y here. And you have that lambda 1 is different from lambda 2. It's 2 different eigenvalues. Now, how am I going to go about this? I will multiply the first equation from the left with the eigenvector y. Remember, y is a column vector, and if you should multiply this vector here, which is a column vector, it's a square matrix times a column vector. So in itself it is a column vector. So you have to have a row vector in order to multiply with this. And a row vector here is the transpose of y. So what I do is I make this product. Like this. And instead of this one here, I can write lambda 1 times x now lambda 1 is a constant. I can put this outside, so I get lambda 1 times y transpose times x. Now, this is a scalar. It's the dot product, in fact, between y and x, so it's a scalar, or the scalar product, and then times a real constant here. I can take the transpose on both sides. What do you get if you transpose a scalar? Get, of course, the same scalar. And so if I transpose on both sides, I get y. And remember how you transpose matrix products. That is, it is the product of the transpose of each of the factors, but in reverse order. So this will be then x transpose A transpose, and then the transpose of y transpose is y itself. So on the right hand side, when you transpose this, you get x transpose times y. But now we can use that. This is in fact symmetric, because we can then write this as X transpose times A times Y, and this is equal to lambda 1, and then X transpose times Y transpose. And here I have used that A is symmetric, so the transpose of A is equal to A. But let me use the other equation here. If I pre-multiply this by the transpose of X, I get, and then times Y. And on the right-hand side, I get lambda 2, and then I get X transpose times Y transpose. And then I can subtract the two equations. If I subtract this from this one, it's the same thing on the right-hand side, so I get a 0. Oh, on the left-hand side, sorry. On the left-hand side, I get 0. And then on the right-hand side, I get lambda 1. This is the same factor, so I can put it outside lambda 1 minus lambda 2. And then times this factor here. Lambda 1 and lambda 2 are different. So this is different from 0. So I can divide by this. And I get that X is equal to 0, because this is actually the scalar product of the two vectors. So in this way, I have proved that for different eigenvalues for a symmetric matrix, the eigenvectors are orthogonal. So this is nice. Let's take, we start again 20 minutes to 12.